Hello and welcome to Toddcast number 29. Going to cover thermodynamic review and between Toddcast 29 through 32, there'll be two covering kinetics, two covering thermodynamics. One will be a review of Gen Chem to get the foundation. The second one will be as it applies to organic chemistry in terms of both the kinetics and the thermodynamics. So it's important in organic chemistry, but we don't do quite as much math. That doesn't mean we don't need to know the implications of numbers and what they tell us, but hopefully you'll see as we go. So that said, I'm going to refer to it as thermochemistry as opposed to thermodynamics. So thermodynamics, I personally see as a physics topic or an engineering topic, the movement of heat. Thermochemistry is a generation or absorption of heat through a chemical reaction, and that's pretty much what we're going to deal with, that as well as free energy. So thermochemistry, energy is associated with a chemical reaction that is generated by the changing of bonds going from reactants to products. So the fundamental graph that just have to know for everything is energy over the course of the reaction, from start of the reaction to the completion of the reaction. And so at the start, we're here. That's going to be our reactants, our solvent, our catalyst, everything we have in there. In the end, these are our products. Again, our solvent, hopefully regenerated catalyst. In the middle, there's a transition state that may involve a catalyst bound to the reactant as it transforms into reactant, or from reactant into product. So the transition state is possibly multiple molecules combined together. It's going to vary from reaction to reaction, but it's our progress from start to finish. Okay. There's a slight difference between the first graph and the second graph. They're both going from start to finish, but you'll notice this one flipped around as this one. So the forward reaction, when done backwards, is the complete opposite. So reactants going to products, you flip around and make the products reactants and reactants products, the reaction shifts. So if it's favorable for energy releasing, heat releasing in the forward direction, then if I look at the reverse reaction, it will be heat absorbing. It should be perfectly symmetric. So the path forward should offset the path backwards. Okay, want to look at these as just conveniently as possible. The kinetic zone, meaning the area where reaction rate can be evaluated, and then the thermodynamic zone, the net energy gain or loss. So if we start high and finish low, if the system goes to a lower energy, then it will release that excess energy. So this would be exergonic or exothermic, depending on whether I'm doing a delta G or delta H graph. And then for the kinetics, the higher the transition state energy, the higher the activation energy, the harder it is for the reaction to go. And typically the higher the temperature you have to add to the system, or you have to do something special to make it work. So again, activation energy is from start to apex. Delta G and delta H are this energy aspect. So want to separate those two. So kinetics, thermodynamics. And the terms I mentioned, exergonic heat, exothermic heat being released, exergonic just free energy, which includes entropy energy as well. Okay. And the opposite of exergonic is endergonic. The opposite of exothermic is endothermic. I do exothermic in red, implying if you touch it, it will feel hot. I do endothermic in blue, implying if you touch it, the reaction flask will feel cold. Okay, we're going to take advantage of that as we go. If you want to shift a reaction one way or the other, you can change the temperature and take advantage of the endothermic and or exothermic nature of it. Okay. So interpreting energy diagrams, there's a lot to these. And so free energy, you can do this axis, I'm going to do delta G this time, and then reaction coordinates start to completion. Again, this is your kinetic, your activation energy aspect, and this is your free energy change. So in this case, if the activation energy is very high and delta G is very low, and that's often the case, then the reaction, the amount of energy it generates won't be enough to propagate the reaction. So in this case, you have to sustain a certain amount of energy in the system. You have to heat it, or you have to provide some way for it to continually have input energy to overcome the activation barrier. Catalysts can help with that situation. Adding heat can add. whatever the scenario is, you may have to dump more energy in one way or another. So it might be an energy inefficient reaction because you'll end up wasting a lot of heat energy if you use a heat bath. Catalyst might be, I don't know, expensive, but you have to do something to make that reaction go. When it's unfavorable, activation energy is very high, and delta G is you have to put energy into it. So this one you definitely have to provide energy. This must be done at a very high temp. So this one, generally elevated temperature, will do some reactions over the course of your lab career that will involve adding a ton of heat to make it go. And those actually sometimes are better reactions because even though they're energetically unfavorable, you can control them better by adjusting the temperature just the right amount. You can control what product is formed compared to another. Okay, this will be the interesting one. We will not be doing this reaction in class, and hopefully, or in lab, and hopefully you can see why. Activation energy is significantly lower than delta G. This is what's known as an explosive reaction. This is one where if the reaction generates 3 times the amount of energy needed to get it to go, then when one reaction goes, it triggers 3 more molecules to react, which in turn turn into 9, turn into 27, 81, 243, and I've exhausted my ability to cube. So the problem with this is that if you have an out of control reaction, you have to run an ice bath or you have to run it in a controlled environment that cannot blow up. And then last but not least, you have this last reaction. This is a lot of our biochemistry, a lot of our body reaction. We don't get a lot of delta G out of it. So if you go over here, you'll notice it's very, very close to being about 1 for K equilibrium. Your products are slightly more favorable. So your equilibrium constant might be, if you're lucky, 10-ish. But the problem is activation energy is so high. So this is good and bad. 1, it means you have something like this, it's reversible, so no damage is permanent. And 2, it takes so much energy to make it start and make the reaction go, activation energy, that it's relatively stable. But if you do need to have a reaction like this run, then you do it in the following way. You add a catalyst to lower the activation energy, and you take the product away. So you take advantage of Le Chatelier's principle. If you remove product, the reaction will go in the forward direction. And so a lot of our pathways involve steps like this, where you barely any energy, but the next step in the pathway pulls that product along, and then this reaction goes simply by the equilibrium aspect. Okay, does it need heat? Yeah, it needs some activation energy, or it needs a catalyst. And then is it favorable? Barely. Okay, mention just briefly that delta G and delta H are similar, but the difference is free energy takes also into account the entropy factor. So hopefully this equation which is in alphabetical order, like everything in chemistry, G, H, and T, if we treat that as one word. So delta G, your free energy change. If it's negative, it's a favorable or spontaneous or exergonic reaction. If it's positive, it's unfavorable or a non-spontaneous endergonic reaction. Delta H tells me about heat. If it's less than 0, a negative number, it's exothermic, meaning heat was released. Positive number, it's endothermic, meaning it feels cold, heat was absorbed. And delta S has to do with the randomness. It is favorable for things to fall apart, totally natural. So if you get disorder, delta S is positive. If you get order, then it is negative. So if you get more order or becomes less random, you had to do work to make that happen. So delta S is negative. And then if it falls apart, delta S is positive. That's chaos is the nature of who we are. Okay, so with these terms, hopefully we can put together some systematic understanding of this. So if delta H is negative, it's a negative value for delta H, and delta S is positive, meaning it's becoming more random, then negative minus a positive is negative plus a negative, that makes it more negative. Delta G is definitely going to be negative, can only be negative no matter what. So that's always going to be a favorable reaction. If it happens to be that the one is positive, one's negative, then a positive number for delta H minus a positive number here means it's now a competition for which one is more significant. So if the temperature goes up, this term becomes a little more significant so that it becomes favorable. The negative outweighs the positive only when the temperature is high. So favorable at high temperatures. So a really good example of that is the boiling of water. When the temperature is below 100, then if you put in for this, the delta H of vaporization equals delta H of vaporization minus T delta S of vaporization. When this number is less than 273, less than 100 Celsius or 273 kelvins, then this positive number will be greater than this negative number. So overall delta G is positive and it will not melt. When it's over 100, then this number becomes so significant that this number is smaller. I'm subtracting bigger number becomes negative. So that T becomes important. When it equals 100, delta G is 0, meaning it can be a liquid or a gas. So it's one of those typical GChem examples we use to demonstrate how important the T delta S term is. Okay, if it's negative and positive, you're going to be in trouble because, or negative, excuse me. So if this is negative and this is negative, that means a positive. So it's going to be the opposite, whereas temperature goes up, it actually becomes less favorable. That's kind of a weird scenario. So that's a reaction we need to run it at low temp in order to make it go. And then finally, positive here and negative here, that's going to be unfavorable no matter what. If positive minus a minus would be plus, plus plus would always be a positive number, unfavorable at all temps. So typically what we're going to run into in OChem will be these three. We will not be using the last reaction. Okay, so let's consider this reaction here. So if I look at this, my first guess, pi bond, but this has some flexibility. This molecule has some flexibility, but a single ion can move around. So entropy, don't know, you're going from two molecules to two molecules. You have a little more freedom in rotation because of this. So it's hard to say what's going on there, but then the bond energy. You have to consider these, the O to carbon bond and the carbon to bromine bond. Well, bromine is very large, it's a weaker bond, so breaking weaker to form a stronger seems like it should be, I don't know, drive it in the forward direction. But entropy, the freedom rotation here and the freedom rotation here probably kind of cancels out, two molecules. So delta S is about 0, meaning delta H and delta G are essentially the same. This I can make a prediction that delta S is trivial enough that only delta H is significant for delta G. This reaction, far more predictable. Two molecules going to one. This one is in a ring, so it's also rigid. It doesn't have as much flexibility. So 2 to 1 delta S, this is definitely getting much more ordered. So delta S is, I want to say, highly negative. So that'd be a situation like this. Probably not going to be terribly favorable to go. So has to be highly, you end up making two new bonds. So you form a pi bond, 2 sigmas, you break a pi and form, you end up going from 3 pi's to 1 pi and 2 sigmas. So your net is gain of 2 sigmas and loss of 2 pi's. Sigma are much more stable, so you'll have a highly exothermic reaction. This is a case where it's purely driven by that reaction, but this is one that is just kind of an interesting, delicate reaction. Because of the delta S factor, you end up not having to get terribly high temperatures to make this go. So this is one we usually do in light, because we do it in light, and keep it at low temperature and give it the energy needed to make it go. So we'll learn as we go. Interesting reactions. Okay, Hess's law, to review that, the sum of your delta H's, your delta G's, or your delta S for any reaction can be obtained by adding any component reaction. So in this case, if you have 3 reactions that add together to make an overall reaction, then you can add up their delta H's, their delta S's, or their delta G's to get the overall delta H, delta S, or delta G. For equilibrium, you must multiply the k-equilibriums to get the overall k-equilibrium. You also probably learned it, delta H of formation of products minus delta H of formation of reactants. We won't really be touching that in this class too much, but we do need to know this sort of approach, that if delta H has or doubles, it's because the reaction halved or doubled, meaning if I take 2 of something plus 2 of something going to 4 of something, I get a certain energy, then 1 to 1 to 2 will be half that energy, or vice versa. So perfect example, 1 nitrogen, 1 oxygen going to 2 NOs would be 180.5 energy in, it's endothermic. If I did half an N2, half an O2, and only went to 1 NO, then it's half the amount. If you reverse the reaction, products going to reactants instead of reactants going to products, then the sign changes. So NO going to N2 and O2, 1/2 of each of them is now negative of that number. And then when you combine multiple reactions, that's this up here. So if I want to combine these 2 reactions to see what I end up getting, I'm going to have my NOs cancel. I'm going to have 1 N2, 1/2 N2, plus 1 O2 going to NO2. And it'll end up being the sum of that reaction. So those cancel, half an N2 plus a full O2 going to an NO2 is going to be about 33 or positive 33 of kilojoules per mole. Okay, just revisiting. Don't want to spend too much time on it, but hopefully it sounds familiar. And then reviewing some math. This actually is imperative. This is how we're going to make some predictions about our reactions. Delta G naught is delta G when starting with standard conditions. We often use it interchangeably with delta G, and we shouldn't. So delta G takes into account where you are when you beginning, in the beginning, where you are when you finish. Delta G says only from standard. So if you think of this, it's more like the overall reaction from start to finish is from the middle. I'm going to call the middle where you have 1 molar of everything. So middle of equilibrium is this delta G. This is, if we go to the middle, then Q would equal 1. So that would log 1 is 0, so that would cancel. So it's only you have at the start. So it's almost like breaking the delta G into 2 parts. The start to the middle where you have 1 of everything, and then the middle to the equilibrium where you lose 1 of everything, go to your final. So overall, if you add these together, start to middle and middle to equilibrium, you get start to equilibrium. So delta G from the initial conditions to the equilibrium, middle conditions onto the equilibrium conditions. So delta G is from start to finish. Delta G naught is from standard to equilibrium. And then this is start to standard. I'm going to say the standard, I consider it in the middle. If we have all reactants, we go to standard, which is a balance of reactants and products, and we finish as all products. That's what I'm visualizing. So if you want to rewrite this as standard, that's perfectly fine as well. But keep in mind, if we start at equilibrium, then equilibrium would equal 0. So standard equilibrium plus equilibrium to standard would cancel. So it works out, whatever you want to call it. Hopefully it seems reasonable to you. Okay, the prediction of which way a reaction goes depending on Q, the way it exists, and K, where it wants to be. So Q is the start, K is the equilibrium finish. Couple perspectives. If K is smaller than Q, that means Q, what I'm starting with, is a case where I too big a numerator, so products are too large, and too small denominator, so R is too small. It has to go from products to reactants to reach equilibrium. So that would be a backwards reaction. Easier than doing that. I can logic my way out, but much easier than doing that. Always draw Q and K alphabetically, like we did here, Q and K. Take this less than sign and turn it into an arrow. So if I turn this into an arrow, that means reaction has to go in that direction. So turn your greater than or less than sign, draw it alphabetically, turn it into an arrow that tells you which way it goes. And then last but not least, the mathematical equation. So just delta G is minus ln of Q, and I'm substituting this in here. So minus RT ln of K. When it's minus, it's a denominator in a natural log. So that's why it's RT ln of Q over K. If Q is bigger than K, it's a number bigger than 1. Log number bigger than 1 is positive. Delta G is positive, so the reaction is unfavorable in the forward direction, so favorable in the reverse direction. So any way you cut it, I am fondest of this one. This is for the math people. This is for the conceptual people. This is for the memorization people. Be who you are. Okay, want to throw a question because this is fair game for OChem, Biochem, or GChem, which means if you go into a standardized test, these are the type of things you have to expect to see because it is so prevalent in multiple sciences. So in this case, we're going to use that same equation we just did, and that is because it's giving me a delta G naught, then I know that number, so it's minus RT ln of K. And minus RT is one of those numbers that, yeah, you can pick it over to, you can figure out with time, but it's usually around 2.5-ish. So I want to figure out what the K equilibrium is. It's products over reactants, ignoring water. And they tell me that inorganic phosphate is 1 molar, so phosphate is going to cancel because that equals 1. So therefore, it's just the diphosphate over the triphosphate. Okay, so now it's time to plug in. So for this reaction, I want to figure out what delta G is, or K is, excuse me. So given a delta G. So RT is around negative 0.25, just one of those facts that you can know. So if I were to take this and divide or multiply accordingly to get rid of the 2.5 and e to the power, I would end up with negative 25 for delta G, negative 2.5. So I'm going to divide each side by negative 2.5, 10, and again, so divide through like I mentioned, and then put e to the power to get rid of ln. E to the 10 is going to be ln of that ratio. E to ln cancels. So the ratio is e to the 10th, choice D. So one of those math questions that you sit there and like, oh, what a pain to pound through. But the numbers aren't bad. Numbers are totally doable. Just one of those things that you just have to learn how to manipulate the math. So this is just why we're going through this. This is something prevalent in GChem, OChem, and Biochem, so we have to cover it. Relating K equilibrium to delta G. Back to the conceptual aspect. Okay, so we're going to look at math, but math more as a conceptual thing to decide kind of favorable, medium favorable, highly favorable, and then the same thing for unfavorable. So solvent is just whatever solvent we're doing this imaginary reaction in. And so we have this relationship. If K equilibrium equals 1, then plugging in RT ln of 1, ln of 1 is 0, so delta G is 0. If it's 10, it's negative 2.3, 100 is negative 4.6. So it ends up that it goes up by about 2.3 because it's E equals 2.3. So 10 to the 2.3, E, excuse me, 2.3 is 10. So this hopefully makes some sort of sense. K equilibrium is greater than 1, so it favors products. K equilibrium is less than 1, so it favors reactants. One thing I do want to point out, if you happen to be working with a couple different OChem textbooks, you'll find this table or one like this in multiple textbooks, and they actually have very different numbers. And so I want to address why mine are different than theirs, and it really is as simple as this. They're saying for one reactant going to one product, then it would be a 10 to 1 ratio, 100 to 1, 1,000 to 1, 10,000 to 1. But reality is you will almost never get one reactant going to one product. It just is just impractical to think that way. It's typically nucleophile, electrophile forming a product and a leaving group. So 2 going to 2 is the most common thing we'll do in OChem. So because K equilibrium equals C times D over A times B, then I want to say 100 of these and 100 of these, and one of these and one of these will give me my 10,000 ratio. So that's why these numbers different. So you may have a book that uses this K as the product ratio number, but that's not necessarily the case. Okay, that was a math review. Hopefully that was useful. The reality is for OChem, you have to know some of those things as quick reference or quick thoughts, but it's not a core part of what you'll be tested on. So hopefully this was a good podcast, and I will see you at the next one. Bye.